textbook. And now today's topic is real numbers. Now first of all we need to know what are real numbers. So taking this diagram, okay, the smallest set we know is a natural number which is contained in whole numbers, which is again contained in integers, then rational numbers. And there is other set of numbers that is irrational number represented by QC, that is the complement of rational numbers. And the collection of all these numbers is called real numbers. So now coming to natural numbers, we have studied in our previous classes that natural numbers are the numbers which starts from 1 and goes on indefinitely. Now the whole numbers are 0 plus all the natural numbers, that is 0, 1, 2, 3 and so on. Now integers is another set which contains the whole number set plus the other negative numbers. Negative numbers are -3, -2, -1 and whole numbers are 0, 1, 2, 3 and so on, also from here. So now coming to the larger set, that is rational numbers. Rational numbers contain our own other sets like natural number, whole number and integers. But there are basically three forms of rational number. And the most important one is the first one, that is P by Q. Where Q can never be 0 and P and Q are co-prime. But now what is this co-prime? Have you ever heard of this? Co-prime. Co-prime numbers are the numbers which are only divisible by 1, which are together only divisible by 1. For example, if I take 2 and 3, 2 is divisible by 1, 3 is divisible by 1, and there is no other number which can divide both. But at the same time, if I take example of 2 and 4, 2 is divisible by 1, 4 is divisible by 1. But these two numbers are also divisible by 2. So these numbers can never be co-prime. And these numbers are co-prime. Now the second form is terminating decimals. Terminating decimals are the decimals which terminates at some time, which ends at some time. Like 2.356. And it doesn't go after this. It stops at this one. Third is non-terminating decimals. Non-terminating repeating decimals. What does repeating mean? It means that after some point the number is repeating itself. That is 2.34, 34, 34, 34 and it goes on continuously. It never ends. It never stops. That's why it's non-terminating. And 34, 34, 34 is repeating itself. That's why it is repeating decimals. Now another set that is and now the another set that is separate from rational numbers is irrational numbers, and it is denoted by QC. Here C means complement, that is different from rational numbers. These again have three forms. First one is the √2, √3, √5. So basically form √p, where p can be any positive integer. But if I take example of √4, is this an irrational number? No, because √4 is nothing but 2 and 2 will be our rational number. So √4, √9, √16, the number inside the root can never be a perfect square. So that's why these all are rational numbers and these are irrational numbers. The second form is non-terminating, non-repeating decimal. What it means, non-terminating, it never stops. Non-repeating, it never repeats itself. Like 2.3412983976. It goes on continuously, but no same pattern is repeated. If we see here, the same pattern was repeating again and again. 3, 4, 3, 4, 3, 4. But here is no pattern going on. So that's why it's a non-terminating repeating decimal and it will be an irrational number. Now third is a pi. 3, 3, 3 and 1. So we can write 135 as 5 into 3 into 3 into 3. Similarly, 225 can be written as 5 into 5 into 3 into 3. So now we are going to make the pairs of a common factor, that is highest common factor, the factors which are common. We can see that this 5 is common, this 3 is common and this 3 is common. So the HCF will be 5 multiplied by 3 multiplied by 3, that is 45. Okay, so this is a very simple method of finding HCF. Now if we find HCF by long division method, okay, the answer will again be same. Now how are we going to do that? We take a larger number inside the divisor and it will be 135 and we are going to divide it. Now we will take 135 at 1, it will be 0, 9. Now this 135 will come here, like this. And again we will divide by 90, it will be 45. Now this 90 will come here, so it will become 90 and it will be completely divided at 2. So the number at which we get the remainder as 0 is the highest common factor, that is this 45. We can see that here we also got the answer as 45. So it doesn't matter by which method you find the HCF, the answer will be same. Now let's come to LCM. LCM is least common multiple. If I take two numbers, suppose I am taking 2 and 5. We need to find the smallest number which is divisible by both. So if I take 10, we can see that 10 is divisible by 2. Similarly, 10 is divisible by 5. And if I take any other number below 10, it is not divisible by both numbers. So this 10 will be LCM of 2 and 5. But how did I found it? It's like this. Okay, taking an example of 135 and 225. Again, we are making the prime factors of it and making the prime factors of 225. So we can write these factors as these. Now we will make the pairs of the common factor. It will be 5, 3 and 3. So LCM will be, we will write these paired number as one unit. Like 5 and 5 will be 5, 3 and 3 will be 3 and 3. And these two numbers are left behind. So we will write them as it is. It will be 3 and 5. Right? So the answer will be 675. This will be the LCM. Now we know that the HCF of this same question was 45. So this LCM and HCF has a rule. What is that rule? The rule is that LCM into HCF will always give the product of these two numbers. That is what I am saying is that 675 into 45 will always be equal to 135 multiplied by 225. This is the rule of LCM and HCF. So now suppose we have a question like this, that x is given as 2 cube 5 square into 3, y is 2 square into 5 and z is 2 to the power 4 and 5 raised to the power 4. So now how are we going to find the LCM and HCF? One way is we can expand them and then again make the pairs, or instead of that we can solve it by this method. Like LCM is the product of largest power of each vector. We can see that there are three vectors, 2, 5 and 3. So LCM will be the largest power of them. Like 2 has the largest power of 4, so the 2 will be raised to the power 4. And similarly 5 also here has 2, here has 1 and here is 4. So the largest power of 5 is again 4. So it will be 5 raised to the power 4. And the largest power of 3 is 1. So we will write 3 raised to the power 1. So it will be the LCM. So all the factors are taken and the largest power of each factor is taken. But in HCF, we will take the smallest power of the common factors only. The common factors here are only 2 and 5. So we will take 2 and 5 but their smallest power. Here we can see that 2 has the smallest power of 2. So we will take it as 2 and 5 has the smallest power of 1. But we will not take 3 here because 3 here is not a common factor because 3 is not included in these two numbers. So these are the method of finding the LCM and the HCF. Our next topic is decimal expansion. We all know what is a decimal expansion. The numbers we write in the form of this point 3, 5, 6. Suppose this ends here, and this kind of number is called a decimal number. So these decimal expansions are divided into two types, that is terminating and non-terminating. And non-terminating is further divided into repeating and non-repeating. Terminating means the decimal expansion which ends somewhere like 2.53. That's it. It ends here, so it is a terminating number. So non-terminating repeating. Non-terminating repeating is the number in which after point the numbers have a same pattern which is repeating again and again. Suppose 2.35, 35, 35 and so on. So we can write these numbers as 2.35 bar. Okay? Now third is non-terminating, non-repeating, the numbers which never ends. And also they don't repeat a certain pattern. They are random numbers like 2.3, 4, 1, 7, 3, 9, 8, 6. It's going on randomly and it never ends. Now the question here are how to find the decimal type of decimal expansion without actually dividing them. Suppose we have a terminating decimal expansion. We are given a question like this. We need to find whether it's terminating or non-terminating repeating. What we will do, we will find the denominator. Here we can see the denominator is 213125, right? We will find the prime factors of it. 3125 can be written as 5 raised to the power 5. Now the rule is whenever the denominator is of the form 2 raised to the power n and 5 raised to the power n, that means the denominator should have the factors of either 2 or 5 or 4 but no other factors. Like here we have the factors of 5. No, it doesn't have 2's factor but we can write it as 2 raised to the power 0 also. So this type of expansion will be terminating. But when the denominator is not of this type, then the expansion is not terminating, repeating. For example, we have 29 upon 70. Now the denominator is 70 and 70 can be written as 2 into 5 into 7. We have the factor of 2 and 5 but there is also a 7. So this 7 makes it a non-terminating repeating decimal. So now coming to our next topic, that is irrational number. In this exercise we are going to prove that how a number is irrational or a rational number. So taking a very simple example of root 2. We need to prove that root 2 is irrational. We know that root 2 is irrational but we will be writing a proof for it. And to do that, we will be using a contradiction method. What is a contradiction method? That we take a different thing. We need to find that it's an irrational number. So we will take the exact opposite of it and then we will show that it was wrongly taken and so our proof is done. Okay? So we will take that root 2 is irrational. We need to find it. We need to prove that. So we will take the opposite of it, that root 2 is rational. So we know that the rational number is of the form p by q. So root 2 will be p by q, where p and q are co-prime. So what is a co-prime number? Co-prime number is the number which both are divisible by 1 only. No other number can divide both the numbers. So root 2 will be p by q. We will take q on the other side. It will be root 2 q equals to p. Now we will square both sides. We will be squaring both sides. Root 2 square will be 2, q square and p square. We will take this 2 on the other side. Now we can see that 2 is dividing p square. square is equals to 9. Then 3 divides 9. So 3 also divides 9. A will be 3. So 3 also divides 3. We can take up plenty of examples like this. So we are using this rule over here that if 2 divides p square, then 2 divides p also. Right? If a number 2 divides p, so p should be a multiple of 2. Suppose I say 4, 2 divides 4 or 6. Okay? So now 6 can be written as 2 into 3. So 6 is a multiple of 2. Similarly, if 2 divides p, so p can be written as a multiple of 2. 2 into c, and c is any number you can take of your choice. Now we will put this p in this equation number 1. So it will be 2q square equals to 2c whole square. It will become 2q square equals to 4c square. We will take this 4 on this side and we will cut this 4 by 2. So it will become q square by 2 equals to c square. Now here we can see that 2 divides q square, and by this rule, if 2 divides q square, then 2 divides q also. Right? So we can see that 2 divides p and 2 also divides q. So 2 divides both of them. But p and q are co-prime. So they should be divisible by 1 only. So it means that we have a contradiction. Contradiction means that we have come to a wrong conclusion. That it's a wrong thing with what we have done because it contradicts our assumption. So we will say that root 2 is irrational number because our assumption was wrong. So students, this is the proof of this question, and here the chapter also ends. So keep practicing. Thank you.